Hello, welcome back to our series of current electricity. This is Joseph Mayanja, A-Level Physics, Lesson 2. In this class, we are doing a continuation of our last class where we did the introduction to current electricity. But basically in this class today, we are going to talk about the mechanism of electrical transfer or movement, or the mechanism of electrical conduction, and then we shall talk about the drift velocity of the electrons as they flow across a given point in a given time in a conductor. Mechanism of electrical conduction in metals. We know that metals have electrons. In fact, that is what makes them suitable for connections in electrical circuits. So they have free electrons in the atoms that can easily freely move from one point to another. We are going to consider this circuit. In this circuit, this is our conductor or the metal, and then these are the connecting wires, and then this is our cell. In our previous class, we said that when you have more than one cell in a circuit, then the combination becomes a battery. Consider this cell. We know that this terminal here is a positive terminal, and then this is the negative terminal. And we know that usually current, or what you call convection current, the symbol is I, flows from the positive terminal to the negative terminal. But on the other hand, electrons flow from the negative terminal to the positive terminal. We are going to see why, but we are going to consider this circuit here where we have our metal. The length of the metal here, let us say it is L, and then its cross-sectional area is A. We are saying this metal is cylindrical. Now, we want to understand the mechanism of electrical conduction in metals. How do electrons flow across conductors? What forces them to flow? Which force pushes them to flow across conductors? And how is electricity conducted throughout a metal across the ends of the metal? We are saying we are considering our conductor of cross-sectional area A and length L. We know that these metals have free electrons that are usually in random motion. Since these are metals, in them they are actually atoms. But we know that atoms have what we call the electrons. Those are the negatively charged ions, and then the protons that are positively charged. So if this is atom 1 and this is atom 2, these atoms have what you call the electrons, and they are always free to move because they are vibrating in their mean fixed position in the lattice. But when a battery or a cell is now connected across the ends of that metal, we expect an electric field to be set up. Remember, we said that since this end A of the conductor is connected to the negative terminal, that means that this end is at a negative potential, or what you call a lower potential. And then if this end B is connected to the positive terminal, then it is at a positive potential. It is like positively charged. That means that there is an electric field set up across the ends of that conductor. Let us call it E. That electric field accelerates these conduction electrons, and they gain what we are calling a velocity and kinetic energy. So these electrons, as they are being accelerated by the electric field, and they are accelerated in the opposite direction, they gain velocity and also gain kinetic energy. So as they are flowing, they end up colliding with atoms that are vibrating about their mean fixed positions, and they end up giving up some of their energy to those atoms. So when the process goes on and on, these electrons, for example electron 1 here, shares or gives up some of its energy to the neighboring atoms. Remember also, those neighboring atoms have electrons. The amplitude of vibrations of the atoms increases, and the temperature of the metals is also expected to rise because of the friction in between the atoms as they try to vibrate. The electric field continuously accelerates the free electrons, and on average the electrons drift in opposite direction to the field with what we call a mean velocity, and this mean velocity is what we are calling the drift velocity. The continuous drift of the electrons in the same direction constitutes what we call an electric current, and the current produced is direct current because the direction of flow of these electrons is constant. The electrons flow in this direction of flow of electrons, and it is constant. So in summary, we are saying that metals have free electrons that can easily freely move randomly. When that conductor is connected across a cell or a battery, there is an electric field set up. In this case, that electric field set up will be in this direction. It is this electric field that forces that, because that electric field, it is a force that forces those electrons to move. They gain kinetic energy and velocity, and they move, they flow in this direction. As they move from this direction to this direction, they end up colliding with the neighboring atoms, and they give up some of their energy to these neighboring atoms. So the amplitude of vibration of those atoms increases. Remember, before the collision, they're actually vibrating in their lattice, in their mean fixed positions. But when on collision, they gain some energy, and their amplitude of vibration increases. As the amplitude of vibration increases, even the temperature usually increases. But this electric field force is continuously applying on these free electrons, and on average they drift in the opposite direction of the field with that velocity, what we call the drift velocity or the mean speed. This process is continuous but in the same direction. This constitutes what we call a direct current. An electric current, the continuous drift of the electrons in the same direction, constitutes what we call an electric current, and the current produced is direct current, simply because it flows in the same direction, in one direction, and the flow is constant. Let us talk about the drift velocity of these electrons, what we call the mean speed of these electrons. We are going to consider a conductor in form of a cylinder of length L and cross-sectional area A, having any number of electrons per unit volume. This is very important. N stands for number of electrons per unit volume. Remember, our unit volume is 1 cubic meter, each carrying a charge. So this is our conductor, cross-sectional area A, and the length is L. The volume of that conductor is going to be the product of the area and the length. The number of free electrons in that conductor will be the number of electrons per unit volume, then times the total volume. This gives us the number of free electrons in the whole conductor. Total charge Q of the free electron is going to be the product of the number of free electrons in the whole conductor, then times the charge. Suppose a battery is connected across the ends of the conductor, causing a total charge Q to pass through this conductor in a time t with a drift velocity v. We know that the resulting current will be given by Q divided by time. Remember, we said current is the rate of flow of charge. But remember, total charge Q is n number of free electrons in the conductor per unit volume times the total volume times the charge. But we know that velocity is actually from this. We know that distance L, and then this is speed, and then this is time. So speed, or what we are calling velocity, will be the distance divided by time. So we are trying to look for the mean speed or the velocity of the electrons when they flow across a conductor of length L in time t. But remember, from I being equal to N cross-sectional area length times the charge divided by t, this is what we are calling the velocity. Therefore, I becomes product of the number of electrons per unit volume times the area times the velocity, what we call the mean speed, times the electron charge. Thus, the drift velocity from this equation becomes V being equal to I divided by N times E times A. So in case they tell you to derive expression for drift velocity, then you just have to reach this point. From I being equal to never, we can write that expression by divide by A on both sides. This A goes with that, then you come up with this expression. I divided by A is given another important terminology, and that important terminology or the quantity is what we call the current density. And the current density simply is defined as as the current flowing across a conductor of cross-sectional area A. That is what we call current density, and it is represented or denoted by this symbol J, and it's just the current flowing across a conductor of cross-sectional area A, and that is current density. And they can ask you or easily ask you to define, or they can give you a problem and they want you to calculate current density. In this problem, we have a wire, and we are seeing that wire contains 5 exponent 22 electrons per cubic centimeter and has a cross-sectional area of 1 millimeter squared. If the electrons move along the wire with a metal with a mean drift velocity of 1 meter per second, we are required to calculate the current density and the current in the wire. To try out this, we're gonna need to find out what they have given us in the question. They have given us the number of electrons per cubic centimeter, but we know that N really stands for the number of electrons per cubic meter as per our derivation. Then they have also given us the cross-sectional area, which is 1 millimeter squared, but remember we work with SI units, and the SI unit of area is the meter squared, so we have to convert that to meter squared by dividing by a million. They have also given us the mean drift velocity V, which is 1 millimeter per second, but remember we also work with SI unit. SI unit of velocity is meter per second, so we have to change that to meter per second, from millimeters per second to meters per second, and we just divide by 1000. We want to find out what we are required to calculate current density, but we know that current density can be calculated from that famous formula, I divided by A, I standing for current and A standing for area, which is equal to NEV N standing for electrons per cubic meter, E standing for electron charge, and it is a constant, it is always given. Then V is the mean drift velocity, and it was given as 1 millimeter per second. So when we do the substitution, we shall have this standing for N, which is the number of electrons per cubic meter, then electron charge, which is 1.6 exponent negative 19, and then the mean drift velocity, which is 1 exponent negative 3. So when you put that into calculator, 5 exponent 22 times 10 power 6 times 1.6 exponent negative 19 times 1 exponent negative 3 actually get 8 exponent 6, and the SI units of current density are area per meter squared. Can we try part 2? In part 2 we are required to find the current in the wire, but from the expression of current density J, which is equal to current divided by the area, can actually just cross multiply. We'll make I the subject here, and then it becomes current density times the area, you get current. So in that case, we know the current density, which is 8 exponent 6, and the area is the 1 exponent negative 6. Therefore that one takes us to our answer, which is 8 amperes. Now let us talk about the heating effect of current. We know that in most cases, I think you've realized that in most cases you have a wire put in an electricity source. When you try to feed it, sometimes you feel it is hot. So the question is, what is going on there? That one takes us to what we call the heating effect of current. When a current carrying conductor, you realize that it feels hot. Why is it so? When a PD is applied across the wire, the conduction electrons gain kinetic energy from the applied field. As the electrons drift along the wire in the direction opposite to the field, they collide with the ions and lose some of their kinetic energy to these ions. In return, the ions also vibrate with an increased amplitude, and as a result the temperature of the wire rises due to the collisions between the ions and the atoms. Because they have gained kinetic energy from the neighboring atoms, what happens there is that since they have been simply vibrating in their mean fixed position, because they have gained kinetic energy, their amplitude of vibration will increase, and as they vibrate they end up colliding with one another, and then the amplitude and then the temperature automatically increases because of the friction.